So today we're going to be talking about graphical transformations in section 1.6. And just the transformations that we're going to be talking about are stemming off of our parent functions that we saw back in section 1.3. We had 12 parent functions, so we're going to be looking at what takes place from the parent function to a new function, what different transformations take place. The first one is called a horizontal translation. A horizontal translation takes place over the x-axis. And with a horizontal translation, we are going to have a movement to the left and a movement to the right. So it's going to be moving right or left, hence movement along the x-axis. In a horizontal translation, this affects the x value, and it affects the x value, it affects the function itself. And so we will see a horizontal translation within the function. So it will be affecting the x, so it will be within the function. So here you can see that the translation is represented as c, and if we're moving c, or if we are moving the function to the right by c units, if we're moving to the right, you will notice the translation will be written as a negative. If we are moving the function to the left by c units, we will see it written as a positive. So we are look at it as opposite of c when you have a horizontal translation. It is inside the parentheses, and I'm going to use parentheses as a generic term. It will be inside the function, inside the absolute value bars, inside the parentheses for squaring, inside the parentheses for cubing, underneath the radical for square root. And so that is a horizontal translation when it is so-called inside the function. A vertical translation, on the other hand, takes place outside the function. And this affects, and I'll say outside the parentheses, and again, I'm using the word parentheses as a generic term for being outside the function. It is along the y-axis, which means this is going to be moving up or down. It's going to be going up, and I should go this way. It's going to go up or down on the graph, and therefore we call that the y-axis, moving up and down. And this is outside the parentheses. Vertical translation is important because when you go and you were to sketch this graph on your own, a vertical translation is something that you always do last, is the vertical translation, okay? If you want your graph to come out appropriately, then you need to make sure that that vertical translation is something that you do at the very last step in the order. And the vertical translation, if you're moving up c units, it is represented by a positive. If you're moving down c units, it is represented as a negative. So this is by face value. Whereas a horizontal translation, we take the opposite of it when we put it inside the function, affecting the x value. But the vertical translation is the face value. So if we're moving up, it actually is in the positive direction. If we're moving down, it is actually in the negative direction. Okay, so down here we have just some basic functions and the effect of the h and k on each one of these functions, and then what it does to that. So let's say that we have a vertex with an absolute value of 2, -3. That's just a random point that I'm just pulling out. If I want to write and shift the vertex of a absolute value graph from the origin, 0, 0, from the parent graph, and I want to shift it to a new vertex of 2, -3, I could rewrite this as y equals the absolute value of, that's a positive 2, so inside I take the opposite of it, because the x value in the absolute value is actually h in this position, and then plus k is my y, so I will do a -3 there. This means that I am moving that graph to the right 2 units and down 3 units. To the right 2 units and down 3 units, and I can pull that off of that equation as well. I'm going to do the same thing with the squaring function. picking out just a random point of -4, 1, and I can rewrite that squaring function with a new vertex compared to the parent function, the new vertex being -4, 1, so I would write that function as x. This is a negative, so inside the function I take the opposite, so +4, and the 1 stays the same as +1. This means I am moving to the left 4 units and I'm going up 1 unit. So to the left, I take the opposite of what's inside the function, and for base value, what is outside the function. A cubing function goes and passes through the origin, and that's the point at which I'm going to be looking at and comparing it to. So let's just say we have a new point of -2, 5. So to rewrite that cubing function, inside the parenthesis would be my -2, but I represent that with the opposite. So x plus -2 cubed, 5 is positive, that stays as face value. This means I'm moving to the left 2 and up 5. And understand that on these transformations that I'm doing here, this is comparative to the parent function. Square root starts at the origin. That is its starting point for that parent function. And let's say that we have a new starting point of 5, 7 is where that graph is going to take off. So I would write that as y equals the square root of x, I almost put a y there, x minus 5, I take the opposite again of the x value, plus 7, which means I'm moving to the right 5 and up 7. Here we're given a function, and we're going to look at, just given the equation, kind of like what I did up here, what are the movements of this graph compared to the parent function. So this tells me that I am moving up 4. The second function looks like I'm moving to the left 3 units and down 2 units. And the third one, I am moving to the right 2 units and up 3. So what is inside the function, I take the opposite of. What is outside the function, I take at, and I say the face value, the sign that it is. And inside the function, I'm moving left and right. Outside the function, I am moving up and down. Our third example here is showing us actual graphs of a parent function, which is actually the cubing function. We can see that listed here. And then what I need to do is write a new equation based on the movement from the parent function. So I know that I've got the cubing function here. And here's the point. So if you just recognize one point on that graph and see where that point has moved, that will help us. So here's the point at 0, 0, and it looks like this graph has moved down 3. So I've gone down 3 using that parent function of y equals x cubed. So along the along the y-axis means I'm affecting the y value, which is outside the function. So I get y equals x cubed minus 3. The second one, again, same parent function of cubing. This time it looks like I'm moving to the left 2. So that is along the x-axis, which means I'm working inside the function. And if I'm moving it to the left 2, that means I'm going to have a positive 2 inside that function. I take the opposite on the inside. And my last one looks like I'm moving to the right 3. So therefore, I'm still along the x-axis, which means I'm inside the function. If I'm moving to the right, I change that as a -3 on that. Then if I flip over to the back page, we now are looking at reflections. The front page, we were looking at translations, horizontal and vertical translations affecting the x and the y-axis. Now we're going to be reflecting over those axes. So if I have a reflection across the x-axis, so let's say I've got the x-axis here, and if I'm reflecting over this x-axis, what's actually happening is if this point was here and I'm reflecting it over the x, that point would end up down below. I'm actually moving the graph up and down if I'm reflecting over the x-axis. And because I'm actually moving it over the x-axis, this means it's going to be affecting the y, going along the y-axis, and it will be represented with a negative on the outside of the function. So the negative, which represents the reflection, is going to be outside the function because it actually is moving the graph up and down. If I have a reflection across the y-axis, then if I had a point over here, it would be moving over here. So if you notice, this movement is left and right. So therefore, if it's moving left and right, then it is affecting the x value of that function. So therefore, it is on the inside of the function. Okay, so let's look at these examples that I have here. This looks like outside the function. So therefore, it is reflected across the x-axis. Okay, and that is a squaring function. Now I have the absolute value function. This is again reflected across the x because it is outside the function. It's reflected across the x-axis. And then it looks like I'm moving to the right 3 units and up 2 units. The third one, again, I'm still reflected across the x-axis. And now I'm going left 4 units and down 5 units. Here, we're going to be looking at a graph, parent function of x squared, and we're going to see now what's going to happen with each one of these values out in front. So I'm going to go ahead and on my calculator, I'm going to get the parent function, the squaring function on my calculator, and I'm going to graph that. And I've got the squaring function. Then I'm actually going to be putting in y equals 2x squared. And I'm going to graph that. And you can see that that is a little bit skinnier than the original parent function. We call that a vertical stretch when it looks skinnier. And I can use the word skinnier, I can use the word narrower, whichever word clicks with you, narrower. Then I'm going to put in 4x squared, and I'm going to guess because of, and my bad on that, I'm going to put my 2x squared down here so we can see them all on there. And I'm going to guess that the 4x squared is going to be even more narrow than the other. And the first is my 4, then my parent, and then my 2. And so it is still a vertical stretch by a factor of 4. This is by a factor of 4, that is by a factor of 2. And this one is even more narrow than the 2x squared. Then, let's just for fun add one more to this, and let's put in 0.5x squared, which is 1/2. Wonder what's going to happen with that. And that is even a little bit wider than the others, and I'm going to call that a vertical shrink because it is wider than the parent graph. So it's all, remember, all of these transformations are taking place in respect to the parent graph, and that's our comparison is with a parent graph there. So we come down here, and I'm going to skip over the horizontal, and we're going to look at the vertical. Here we have the factor c being multiplied by the function. And if c is greater than 1, we call that a vertical stretch. If c is less than 1, but I'm going to say also greater than 0, we call that a vertical shrink. So anything from 0 to 1, any fraction in that where the numerator is smaller than the denominator, we will have a vertical shrink. Now, if we want to write an equation with a vertical stretch by a factor of 4 with a parent function of x cubed plus 3, I could say y equals 4 times x cubed plus 3, because that is my vertical stretch by a factor of 4. Let's say we have this equation down here. Y equals opposite of 3 times the quantity x plus 2 quantity squared minus 4. And I would like to write all of the transformations that take place. I see this negative out in front of this 3, and you must be very careful to look at this not as negative 3, but as a reflection over the x-axis would be my first translation that would be taking place. And then once that's completed, then I can see and look at that 3 as actually a stretch because c is greater than 1. The negative represents the reflection, not as negative 3 that's less than 1. And so therefore I have a shrink. This is actually a vertical stretch by a factor of 3. And the reflection is just out in front. Then my next translation would be a movement of left 2 units and a movement down of 4 units. That is a summary of section 1.6 on transformations.